Hey everybody, here we're going to be talking about section 4.3. That is the graphs of sine and cosine. Okay. So as we saw when we were creating the unit circle, we have you may want to have that handy. I have a here is a diagram of the unit circle. So this is what we created in class a couple weeks ago. So you can see here we have various angles for different angles, and then we calculated the sine and cosine of each of those using some triangles. So you can see, remember that the x-coordinate of the point for which this angle hits the unit circle, that x-coordinate is the cosine of that angle, and the sine is the y-coordinate of that angle. Okay. So what we're going to be doing here is kind of transferring these points for sine and cosine to a two-dimensional graph in the xy plane. So here we see that the domain of f of x equals sine x and g of x equals cosine x is negative infinity to infinity. Okay? Because again, we can just go around the unit circle forever and ever, plugging in these angles, right? Where x represents some angle and f of x, or g of x, is the corresponding coordinate from the unit circle. Okay? So we'll basically be making the graphs of sine of x and cos of x if we were to consider them as functions. We also note from the unit circle that the range of both sine and cosine are -1 to 1. So let's take a look at that. So if you look back at your unit circle, here, we can see that if we could just consider the cosine function, so cosine, remember, is the x-coordinate of each of these points. So here the cosine is 1. Here the cosine is the square root of 3 over 2, the square root of 2 over 2, and 1/2. So you can see that the x-coordinate is decreasing as we increase the angle to 90 degrees, or pi over 2. Here the cosine is 0. The x-coordinate then continues to decrease until we get to 180 degrees at -1. So the biggest that cosine can ever be is +1, and the smallest it can ever be is -1. Therefore, its range is from -1 to 1. The same thing can be considered with sine. The biggest that sine gets is at 90 degrees. That's when the y-coordinate here is 1. And the lowest it can be is -1. So we see here that the sine and cosine both have range -1 to 1. And we also notice that if we just continue to go around the unit circle over and over and over and over again, we get basically the same values for sine and cosine. So we say that the trigonometric functions are periodic. So we say that the trigonometric functions are periodic functions. Okay? Because they repeat themselves over and over again. Okay. So let's look at the graph of the basic sine function. Graph of the basic sine function. All right, so what we want to do is create a table of values for the sine function by simply pulling these values off of the unit circle for various angles, okay? So what I'm going to do is set up a table of values. So let's say x and f of x. Because our basic sine function will define as f of x equals 2 sine x, right? So we can make a table kind of this way, all right? So what I'm going to do is try to pull off the easiest of the values. The easiest values occur at 0, pi over 2, pi, 3 pi over 2, and 2 pi finally. Now I've left some space in here just in case we need to fill in some additional points for angles, okay? So let's consider the what the sine is when x is 0. So that means when the angle is 0, what is the value of sine? So let's look. We have at 0 degrees or 0 radians, the sine is simply the y-coordinate of this point. So the sine of 0 is 0. So on my table here, we know that the sine of 0 is 0. Now going to pi over 2. For the angle pi over 2, the sine is 1. So I'm going to fill that in on my table. We also see the sine of pi is negative 1. Excuse me, the sine of pi is 0, y-coordinate. Continuing around, at 3 pi over 2, our sine is negative 1. So you can see some nice alternation in your table. And finally, if we're back at 2 pi, that's the same at 0. So we're back to 0. So for our table of values, we know the sine of 0 is 0. At pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's negative 1. And at 2 pi, it's 0 again. So here we have one full period of the sine function, right? Because it started at this point, which was 0, 0. Alternated a bit here, and then we got back to the same coterminal angle at 2 pi and gave us a value of 0. So if we continued on past 2 pi, we would see this same trend over and over and over again forever and ever. Okay? So let's graph these points and see what we get. So I'm going to start, here's my y-axis, and then I'm going to make a large x-axis there. Okay? So here's x, here's y. And what I'm going to do is scale this axis in a bit of a different way than we normally are used to. Okay? Because my x values, I have to use these angle representations. I want to scale it so that it has these radian values along the x-axis. So what I'm going to do here, I'll put 2 pi here. Okay. And then halfway would be pi, right? It's 2 pi, halfway would be pi. And then halfway between 0 and pi would be pi over 2. So 3 pi over 2 would go right here. Okay. We also know that the range is just from -1 to 1. So I'm going to put 1 there and then -1 here. So plotting the points from our table, we get the point at the origin, which is 0, 0. The point pi over 2, comma 1. So pi over 2, 1. At pi, the sign would be 0. And then at 3 pi over 2, -1. And then at 2 pi, back to 0. Okay. So you can see some oscillation here, right? So is it maybe a straight line that connects these 2 points, or is it kind of a curved line that connects those 2 points? Well, it's hard to see here, but we can fill in some values from the unit circle. So I'm going to go up here and fill in a few values and see what happens. So I'm going to look at the value at pi over 4 as well. The value at pi over 4, if you look at your unit circle, is the square root of 2 over 2. Right, the value at pi over 4 is root 2 over 2. This is approximately 0.7. Okay? I'm going to fill in a value in between pi over 2 and pi now. The pi over 4 angle between pi over 2 and pi is 3 pi over 4. It just so happens that the sine at 3 pi over 4, that y-coordinate of the point on the unit circle, is also the square root of 2 over 2, or approximately 0.7. Okay. So let's plot those 2 points approximately. So that pi over 4 is halfway between pi over 2 and 0. So pi over 4 would be right about there. And 3 pi over 4 would be right about there. So we just kind of estimate 0.7, maybe right around here, and there as well. So if we were to connect the dots here, we would see kind of a curve going up to 1, turning around, and going through 0. In fact, that's exactly what the sine function looks like on those angles. So if we draw a smooth curve there, and in fact, if we go to the bottom half of that unit circle, we would get another curve like that. Okay. So the sine function kind of makes a wave, right? Now, if we were to continue this on, we would just be going around the unit circle again. So we would have another wave of the sine function that looks exactly the same, going between 2 pi and 4 pi, actually. So here would be 3 pi. Halfway between that would be 2.5 pi, or 5 pi over 2. And then between 3 pi and 4 pi, 7 pi over 2. So we get exactly the same look at this. It's periodic. So we know that from this point, the next half pi unit up, we're at 1. So at 5 pi over 2, we would be again at 1. 3 pi would be kind of 2 steps away in the right-hand side direction. So we'd be back at 0. And then you guessed it, at this point, at this value of x, the sine would be -1. And then at 4 pi, kind of mimics this point here, would be back at 0. So you can see another wave, I'm going to dot this one, of the sine function in that direction. And this guy just continues on and on and on forever and ever and ever. We can go kind of backwards as well. So we should have an equivalent wave in between -2 pi and 0. We'll have another sine wave there. So if we break that up, halfway would be -pi and -pi/2. And then here would be -3pi/2. So, let's think about what the value -pi/2 would be, all right? So here we're kind of traversing backwards. So basically, this point 0 kind of corresponds to this point 2 pi. So if we go one kind of half step backwards, we're at -1. So in fact, the value of sine at -pi/2 is -1. So we're kind of like, we're here on the wave when we're here. Then we would go backwards a half step, we get to 0. So we go backwards a half step, we get to 0. And going back, we would get +1, and then back to 0. So we'd have an equivalent sine curve, sine wave there. Looks exactly the same. And that continues on and on and on. So down, and then up, so on and so forth forever. So it's just this oscillating wave, starting at the origin, going up to 1, back through 0, down to -1, and continuing forever. Okay? We see here that the graph repeats every 2 pi units. Therefore, the period of f of x equals sine x is 2 pi. We also see that the height of this wave, the height here, or here, the maximum height that it gets from the axis of symmetry there is 1. We call this the amplitude. Okay? So the amplitude of f of x equals sine x is 1. Okay, amplitude. All right, now let's look at the cosine function. So let's look at the graph of the basic cosine function. Let's say that's g of x equals cosine, cos x. Okay. So we'll do the same thing. We'll make a table of values. So let's start at x, and then g of x is here. And we'll pick these numbers off the unit circle like we did before. Okay. So let's go 0 and count by pi/2. It's pi/2, pi, 3 pi/2, 2 pi. All right, so let's look at our unit circle. So here we see the unit circle. Now we're going to traverse the unit circle the same way we did, except we're going to start collecting the x-coordinates of those points instead of the y's, because we know that the cosine of x is representative of the x-coordinate from the unit circle. So the cosine at 0 would be 1. The cosine at pi/2 is 0. At pi it's -1. At 3 pi/2 it's 0 again. And then back to 1. So let's fill in our table. and then we'll plot those points. So the cosine at 0 was 1. At pi over 2, it is 0. At pi, it's negative 1. At 3 pi over 2, it was 0 again. And back to 2 pi, it's coterminal with 0, so that should give us the same point. So 1. Okay. So let's do a graph like we've done before. Here's our x-axis and our y-axis. I'm going to scale it in the same way I did before. So we know that cosine only runs between positive 1 and negative 1. And let's scale our axis accordingly. So let's say here's 2 pi. Halfway would be pi. Halfway would be pi over 2. And 3 pi over 2 is sitting right in the middle. There. I'm going to scale this side as well. So let's go back to negative 2 pi. Halfway would be negative pi. Half of that would be negative pi over 2. And of course, negative 3 pi over 2 here. All right, so let's plot our points for one period of the cosine function. So 0, 1 is our starting point here. So instead of starting at the origin like sine did, he starts cosine starts at the y-intercept of 1. Now following, so that's as high as it can get. So it's got to go back down from there. So back down, it's got to go through 0, then negative 1, back up to 0, then positive 1 again. So you can see we get kind of an equivalent looking wave. So it bends sort of like this. So here is one period of the cosine function. Right? Of course, it continues to do its thing forever and ever as we go around the unit circle. So it's going to go down like that, back up, and can keep going forever and ever and ever. All right? We can also go backwards. So here we have we're at positive 1. So let's think about what the coordinate is going to be at negative pi over 2. Well, if we look at the trend here, we've always got to go back through the axis. So we know that's going to hit at 0. Then we're on the downward slope here, so we've got to hit negative 1. And then back up. Can't go past negative 1, right? And then back up to 1. So we should get an equivalent looking cosine curve. I'll dot this one too. Much like that. And of course, it continues forever and ever, just oscillating between negative 1 and 1. So we can see a big comparison between the two, right? So here we have both sine and cosine. Right, here's sine in blue there. So you can see it's a wave oscillating between negative 1 and 1. But the starting point is at 0. Cosine, on the other hand, is an oscillating wave going between negative 1 and 1, but it starts at 1 here and then does its thing. Okay. So we can see the period of cosine, g of x equals cosine x, is also 2 pi. And the amplitude, remember that's the distance between the axis and the peak, kind of like the frequency of this wave, is the amplitude is also 1 for basic cosine. Okay. We can also see definitive . 2 pi. information about the intercepts of each of these things, right? So let's do an example. Find all of the x-intercepts of f of x equals sine x and g of x equals cosine x. Okay. So let's take a look. So for sine x over here, let's say, cosine x over here. All right, so let's look back at the graph of sine. So here is your sine curve, and let's locate all of the intercepts. So it looks like here the first x-intercept we graphed was 0, and then pi, and then 2 pi, and then 3 pi, and then 4 pi. We go kind of in reverse. It's negative 1 pi, negative 2 pi. This one would be negative 3 pi, you guessed it, right? And so on and so forth forever. So we can generalize the location of these intercepts, all right? So all of the x-intercepts occur at x equal to any multiple of pi. So we'll say n pi, n times pi, where n equals negative 1, 0, 1, 2, so on and so forth, and in the reverse sense. So all the x-intercepts of sine are at n pi. Now, if we look at the x-intercepts for cosine, let's look back up here. Looks like they're happening at pi over 2, 3 pi over 2. This one would be 5 pi over 2, and so on. And if we go in the reverse, it's negative 1 pi over 2, negative 3 pi over 2, negative 5 pi over 2. Okay. So the x-intercepts of the cosine function happen, it looks like, at odd multiples of the pi over 2's, right? So this one's going to be a little trickier. So the x-intercepts occur at odd multiples of pi over 2. So how do we write that mathematically? Using maybe n as our 1, 2, 3, 4, 5, that kind of thing. So to get an odd number, any odd number can be represented by an even number plus 1, right? So if I multiply n by 2, any number, any whole number times 2 gives me an even number, right? And if I increase that by 1, I get an odd number. So once again, 2 times n is even, add 1 to it, that's odd, times pi over 2. Again, n is negative 1, 0, 1, 2, so on and so forth. Now what I like to do is just make a table of the properties of sine and cosine so that we can have easy access to them. So what I'm going to do is I'm going to take a regular sheet of paper and just turn it sideways like this. And let's title it Properties of trig graphs. So I'm going to make a few columns here. So the first one will be the property And then we'll look at various functions. So let's say y equals sine x is one, y equals cosine x. And then I'm just going to fill in the rest of them. We'll take care of those in subsequent video lectures, okay? So I'm going to do one for tangent, cotangent, secant, and cosecant. Okay. So make some columns here. Right. So let's look at the first property, the domain. And second, we'll look at the range, the period, whether the function is even or odd, the zeros, and any asymptotes. We'll see that some of these guys have some asymptotes we'll have to take care of, okay? So, we know that the domain and range for sine and cosine, remember we can just go around the unit circle and get values, all we want, is all reals, or negative infinity to infinity, okay? The range for each of these is negative 1 to 1. We saw that the period, or how the frequency of which they repeated themselves, was every 2 pi units. So every 2 pi, we get to start another identical wave of each of those functions. Now, if we consider whether they're even or odd, remember that even functions are symmetric about the y-axis. So let's take a look back at sine. Odd functions are symmetric about the origin, right? So let's think about this. If we were to take this curve and fold our paper along the y-axis, where my pencil is, would we get an equivalent matching, some symmetry on either side? And the answer would be no, right? However, if I spin this entire curve around the origin, they basically flip this paper upside down, I get exactly the same looking curve. Therefore, the sine function is symmetric about the origin. Thus, it is an odd function. Taking a look at cosine, here's cosine. Note that if we were to fold this along the y-axis, we would get a perfect match on either side. Therefore, cosine is an even function. The zeros we calculated previously were n pi, x equals to n pi for sine, and x was equal to 2n plus 1 pi over 2 for cosine. And of course, we don't have any asymptotes. The subsequent trig functions may have some asymptotes we'll have to deal with. Okay? So now I'd like to look at how we graph transformations on the trig functions. So save this for later. So we're going to look at variations of the graphs. Okay. So as we saw in chapter 2 and 3, we can obtain variations on the graphs of various functions by using transformations, right? So we can obtain variations of the basic sine and cosine curves using transformations. Okay? This helps to graph functions in the form 1, y equals a times the sine of bx plus c plus d, or y equals a times the sine of, times the cosine of bx plus c plus d. Okay. So you saw previously that these different parameters have different effects on the graphs of functions, right? Luckily, the A, B, C, D parameters, if you can remember from doing transformations, do pretty much the same thing, right? So A controls vertical stretches or compressions and reflections across the x-axis. And these affect the y-coordinate. Of the parent function. B controls horizontal stretches or shrinks or compressions and reflections across the y-axis. These affects the x-coordinate of the parent in an opposite fashion. We'll get to more of what that means. Okay. Oh, and by the way, A also affects the amplitude, changes amplitude if it's different from 1. B can change the period of changes period of our trig function. Okay. C, remember that the C value dealt with horizontal shifts, right? So this tells us info about horizontal shifts. And of course that affects x-coordinates in the opposite fashion as well. And recall that D, from our equation here, tells us info is the value of the vertical shift and it affects y coordinates in the parent. Okay. So all these values do the same, control the same kind of things, and because we have talked about the amplitude, we know that A will change the amplitude for these trig functions, B will change the period here. Okay. So let's try a couple of examples. So first example, we want to graph the following using transformations. Then find the amplitude, period, range, and intercepts. Okay, so let's start with the first one. Y equals 4 sine x. Okay. So comparing here, it looks like we have a value that's taking the place of A, and then B is 1, C is 0, D is 0, right? So it looks like we just have a change in the amplitude of the function, okay? So let's see how transformations can help us graph this pretty easily, all right? So here we're going to consider the parent function to be the sine function, okay? So let's regenerate the table of values for the sine function. So x and f of x here for our sine function. So remember, we go 0 to 2 pi, count by pi over 2's. So we'll start at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. So this is just the regular old sine function. Okay. Now, what were the values for sine? Well, let's think about it. Remember, sine started at the origin, right? So 0, 0, then goes up. 1, then back to 0, down to -1, and then back to 0. So we're always going to use these basic 5 points to graph the parent, okay? So now what does transformations tell us to do? So we want to, so here are our y values. So note that the 4 is going to affect the y coordinates only. So when we do our transformation, our x's are going to stay the same, but we're going to have 4y. Okay. So x's stay the same, 0, pi over 2, pi, 3 pi over 2, and 2 pi. But then that 4 is just going to multiply all of those y coordinates by 4. So 0 times 4 is 0, 4 times 1 is 4, 4 times 0 is 0, -1 times 4 is -4, and then 0. All right? So now we just have to graph these points. So let's say we have 1, 2, 3, 4. We know our amplitudes, our y values go up to 4 and go down to -4. 4, -4. And then let's scale it 0 to 2 pi, pi in the middle, pi over 2, 3 pi over 2. It's pi. Let's go a period in the reverse direction. -2 pi, -pi, -pi over 2, -3 pi over 2. All right? All right, so what I'm going to do, I'm going to graph both the sine function and the 4 sine function on the same grid, okay? So first I'm going to graph the parent function points, and then we'll see how the corresponding transformation has changed it, right? So the basic sine graph starts at 0, goes up to 1, back to 0, down to -1, back to 0. So our basic sine curve looks like this, kind of collapsed a little bit. And of course it will go in the opposite direction, since it's periodic, look exactly the same. So in green here I have y equals sine x. That's a parent function for sine. Now let's see how it changes when I multiply that sine by 4. So now I'm going to plot all the transform function points. So I still have a point at 0, 0. At pi over 2, I'm now at 4. Pi is 0 again. Then down to -4 when x is 3 pi over 2. And back to 2 pi. So you can see that my sine curve has gotten taller. You have a change in the amplitude. Looks like that. We'd have a similar looking curve here. So if I go back, I'll be at -pi over 4. Again, kind of going back this way. Then to 0, +4, back to 0. Have the equivalent sine curve like that. Okay. So we can see the comparison. Really the only thing that has changed, we still look like a wave, right? But the amplitude has just gotten taller because we've multiplied everybody by 4. So let's go back up here, or we can actually go here and list all of those values we need. So the amplitude is 4. The period, when does it start to repeat itself? We're looking at the purple curve here. It repeats every 2 pi units. And our range. The range, remember, is the y values, so how we go as low as -4 and then go as high as +4, inclusive, because we have points that have -4 and 4 as their y coordinates. And our intercepts. Intercepts occur at 0, 1 pi, 2 pi, and then the next one would be 3 pi if we follow that pattern. So it's n pi. Again, of course, n is ... -1, 0, 1, 2, ... It's an integer. Okay. Let's try another one. Let's look at same thing, but we want to do y equals to cosine x plus 1. Okay. So this time we're dealing with the cosine as the parent function, and we see changes to the parameters a and this parameter, which would be d, because it's not inside with the x, it's outside. So remember that a affects y, and also d affects y. So let's think about our transformed parent. This would be y equals cosine x. And let's list our appropriate values. 0, pi over 2, pi, 3 pi over 2, and 2 pi. How do you think back to the cosine? Cosine started up top, right? So when x was 0, we were up higher than the origin at 1. So then we have to go back down. So we know all the values are 1, 0, or -1. So we've got to hit 0, going down, then -1, back up to 0, then back to 1. Now when we do our transformation here, We know that 2 represents a vertical stretch of 2, and D helps us actually vertically shifts the graph of the parent function. So both of these things are affecting the y coordinates. So the x's will stay the same, but my y's will be 2 times y plus 1. Okay. So x's stay the same, so we'll rewrite those. And then we need to multiply the y coordinate by 2 and then add 1 to it. So 2 times 1 is 2, plus 1 would give us 3. Pi over 2, so 2 times 0 is 0, plus 1 is 1. 2 times negative 1 is negative 2, plus 1 is negative 1. 0 times 2 is 0, plus 1 is 1. And 1 times 2 is 2, plus 1 is 3. So we get the same kind of pattern. Kind of starts high, goes down, goes real low, goes back up, right? So let's graph those points there. So we need to go as high as 3, so let's say 1, 2, 3, and then negative 1 down here. And look, nothing's changed along the x-axis, so let's just do our usual 2 pi, pi, pi over 2, 3 pi over 2. And we'll do another period back here, so negative 2 pi, negative pi over 2, negative 3 pi over 2. Okay? Now let's graph we'll graph the original and the transformed graph here. So our cosine, remember, started at 1, 0, negative 1, 0, 1. That's the parent cosine function. And of course it went back the other way as well. Same kind of thing. All right, continue. So there's the original cosine function. Now let's graph our transformed points. So when x is 0, we're now at 3. Pi over 2 is 1. Pi is negative 1. 3 pi over 2 back to positive 1. 2 pi is at 3. So here we have our transformed function. And of course that would continue the pattern in the opposite direction. So here we're back at 1, down to negative 1, up to 1, up to 3. Of course, and that would continue on. So let's think about what our amplitude and things are. So if you notice, the shift kind of creates this axis along which it kind of bounces between, right? So you can see here that the amplitude is the distance from that kind of imaginary axis line to the highest point or the lowest point here, either direction, right? So you can see that our amplitude is 1, 2. It's simply that number that is multiplying out in front. So our amplitude for the function would be 2. So let's write that. Amplitude is 2. Period is, remember, however long it takes to start repeating. In this case, it starts repeating after 2 pi units again. We have not changed anything involving the period here. The range for our transform function. Well, how low can we go? -1. And the highest we get is 3. So -1 to 3. And lastly, our intercepts. These are a little tougher to get, right? So we'll just leave those for now, right? So they're going to be here, here, so on and so forth, okay? But let's say not applicable. Let's say hard to get. All right. All right, let's do a couple more. All right, same thing. We want to graph this guy. Y equals the cosine of x minus pi over 2. All right. So it looks as though we are within the x here. So here we're dealing with a horizontal shift of pi over 2 units, okay? Horizontal shift of pi over 2 units. So let's think. Let's do our original cosine graph. So we're going to use the same old points, 0, pi over 2, pi, 3 pi over 2, 2 pi. And remember, cosine starts high, so we're going to go 1, then down. 0, -1, back up. 0, 1. Now remember that the c values affect x in an opposite sense. So even though we see a minus there, it's actually a shift to the right pi over 2 units, right? So here, this affects the x-coordinate in the opposite sense. So we're going to add pi over 2 to x. There's no parameter outside here, so nothing in y changes. So all the y's are going to stay the same this time. Okay. So the y's again stay the same. So that would be 0, 1, -1, 0, 1. And all the x's, we're going to add a half pi to them. So 0 plus a half pi is pi over 2. Pi over 2 plus pi over 2 is pi. Pi plus pi over 2 is 3 pi over 2. 3 pi over 2 plus pi is 2 pi. And 2 pi plus pi over 2 is 5 pi over 2. And we can generate those graph. Okay. Looks like we're only going between -1 and 1. And this time we kind of got to start a little further to the right. So we'll still put our 2 pi up here. Pi over 2, 3 pi over 2. We also need a 5 pi over 2 here as well. Okay. And we can go in the reverse direction again. Scaling our axis accordingly. Okay. So here I'll just draw the transformed function. So pi over 2, 1. Pi comma 0. 3 pi over 2, -1. Back to 0, back to 1. So it looks exactly like our cosine function. However, it's just been shifted over to the right pi over 2 units, right? So let's think. What would the value of the point be here? Well, it would be 0, right? 0. And then -1, back to 0, to +1, back to 0, to -1, so on and so forth. This is y equals cos of x minus pi over 2. Well, if you notice, this looks pretty familiar, right? This is actually the sine function. So cosine and sine are just different by a horizontal shift of pi over 2 units. Okay. We can get the amplitude and things pretty easily because they're just all the same as sine. Amplitude is 1. That's this distance here or here. The period is 2 pi. Our range is -1 to 1. And our intercepts, x-intercepts, are those of sine. So you can see here 0, 1 pi, 2 pi would be 3 pi, so n pi. Okay. All right, one last example. Let's do the y equals 3 sine of 2x minus pi over 3. So again, we're doing y equals 3 times the sine of 2x minus pi over 3. And we just got to be a little careful here because what we want to do first and foremost is factor off this 2, all right? So here's what I'm going to do. I'm going to factor out that 2. So 3 sine. Here's what's going to happen. I'm going to factor off that 2, and I'll be left with x minus. Now if I factor off 2 from pi over 3, I'll get a pi over 6. I'm just dividing off that 2. Okay. Now why did I do this? So the reason why I did this is because in order to see the true horizontal shift, we have to factor off this value if it's something other than 1. So we always have to do that in order to see the true horizontal shift, or the phase shift, for our problem. Okay? So, let's set up our parent function, y equals sine x. And we use the same values, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Sine, remember, starts at the origin, so 0, and then goes up. So up to 1, then it's got to turn around. Back to 0, down to -1, back up to 0. Now let's handle our transformations. So let's think about what's happening here. So I know that there's only one thing affecting the y value, right? And that is this 3 out here. So I know my y's are all going to just be multiplied by 3. And there are 2 things affecting the x value, right? And be careful, remember we want to do the opposite effect. So here this 2 is going to be multiplying by x. So what I want to do first is divide x by 2. X divided by 2. And then I see minus pi over 6, so I'm going to add pi over 6. Okay. So the y column is very easy. 0, 3, 0, -3, 0. Just multiply all those y's by 3. Now, I need to perform those operations on our x there, okay? So let's see. Here we have 0 divided by 2 is 0, plus pi over 6 would give us pi over 6. Okay? Now, pi over 2 divided by 2 is pi over 4. and pi over 4 plus pi over 6. So again, for this guy right here, we're doing pi over 2 divided by 2 plus pi over 6, right? Which is pi over 4 plus pi over 6. Now if we're adding these, we can cheat a little bit here. Let's do this. What is 1/4 plus 1/6? What is 1/4 plus 1/6? And your calculator can actually turn to a fraction. This is 5/12. 5 pi over 12. Now let's try it for pi. Pi divided by 2 is pi over 2 plus pi over 6. What is 1/2 plus 1/6? That's 2/3. So this is 2 pi over 3. So continuing on, you can check that these values are correct. This would be 11 pi over 12. And then this value would be 7 pi over 6. So let's scale. Here we need to go, the highest we go is 3, the lowest we go is -3 on the y-axis. 1, 2, 3, 1, 2, 3. And let's scale here, 2 pi, pi, pi over 2, 3 pi over 2. I'll just stick with 1 period for this one, this time. And then we want to get these values as well. So these are a little tough to get with this breakdown, but we can just kind of assume. So we know that pi over 6 is less than pi over 2, so let's just say pi over 6 is right here. 5 pi over 12 is also less than pi over 2, so let's say 5 pi over 12 is there. 2 pi over 3 is bigger than pi over 2, so 2 pi over 3 is here. 11 pi over 12 is not quite pi, so 11 pi over 12 is there. And 7 pi over 6 is just bigger than pi, so 7 pi over 6 is right here. So let me do those in a different color so we can keep track. There, 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 there. Okay. So let's plot our points. Pi over 6, 3. Excuse me. Pi over 6, 0. 5 pi over 12 is 3. 2 pi over 3 is 0 again. Then down to -3. Then up to 7 pi over 6. So here we have this sine curve there. So you can see it has the same kind of orientation. It starts at 0, goes up, goes back down, that kind of thing. Okay? The amplitude is how tall it gets from the axis of symmetry, right? So here, that would be 3. Period is, now the period is in between pi over 6 and 7 pi over 6, right? In fact, the period can always be calculated by doing the original period, which is 2 pi, divided by the b value, which is 2 here. So that would be pi. Lastly, the range is -3 to 3. And looks like the intercepts happen at very weird values too. So we'll just say too hard to get for now. A lot of applications come out of these sine and cosine curves. So you can expect lots of things in nature that act like waves, like actual waves, like tide, ocean currents, that kind of thing. Electricity can be modeled by sine and cosine waves, sound, light, etc., etc.